Hello. This will be a demonstration of Proposition 2 from Book 8 of Euclid's Elements, which requires us to find numbers in continued proportion, as many as prescribed, least in a given ratio. We explored in the previous Proposition 8.1 what exactly continued proportion means and what exactly it means to be least in continued proportion. So if those ideas are still foggy in your head, just refer to the previous video. All we're given is just some ratio, A to B. A to B will be our given ratio. And according to this ratio, the task before us is to find numbers in continued proportion, as many as prescribed, least, which have the same ratio as A and B. And the prescribed amount of numbers that we want in our sequences will be 3 and 4. So we want a sequence of 3 numbers which are in continued proportion and which have the ratio of A to B. And we also want 4 numbers in continued proportion which have the ratio A to B, and both of which are the least continued proportions with that ratio. We're going to begin by squaring A. So A times A will make C. Next, A times B will make D, and B squared will make E. So B times B makes E. Furthermore, we're going to have A cubed. So A times A, or A times C will make F. Then A multiplied by D and E will make G and H respectively. So A times D will make G, and A times E will make H. And finally, we're going to take the cube on B. So B times B times B, or in other words, B times E will make K. Now, because A has been multiplied by 2 numbers to make 2 other numbers, namely that A has been multiplied by A and B to make C and D respectively, we can say by Proposition 7.17 that the numbers multiplied have the same ratio as the products. What that means for us here is that A is to B just as C is to D. Next, we realize that A and B both multiply the number B to make 2 other numbers, D and E. And so we can say by Proposition 7.18 that the multipliers will have the same ratio as the products. In this case, that means that A is to B just as D is to E. But remember that A is to B just as C is to D also. So these 2 ratios, C to D and D to E, are the same with the same ratio. So just a property of numbers, they're the same with one another. So we can say that C is to D just as D is to E. So that C, D, and E are in continued proportion and have the ratio of A to B. Next, because A has been multiplied by C and D to make F and G, we can again say by Proposition 7.17 that the multiplied numbers have the same ratio as the products. That is that C is to D just as F is to G. But again, you'll remember in the second step, we proved that C is to D just as A is to B. And so these 2 ratios, C to D and F to G, these 2 ratios, A to B and F to G, are the same with the same ratio, that is C to D. So property of numbers, they'll be the same with one another, so that A is to B just as F is to G. And for the same reason, D is to E just as G is to H. Because remember that A has been multiplied by D and E to make G and H. So again, by use of Proposition 7.17, D is to E just as G is to H. But again, you'll remember in step 3, we proved that D is to E just as A is to B. And so these 2 ratios, A to B and F to G, are the same with the same ratio, D to E. So property of numbers, they're the same with one another, so that A is to B just as G is to H. Finally, because A and B have both been multiplied by the same number E to make 2 other numbers, namely H and K, so remember A times E makes H, and B cubed, that is B times B squared, which is E, so B times E makes K. So A and B, both times E, make H and K respectively. And so we can say by Proposition 7.18 that the multipliers have the same ratio as the products. That is that A is to B just as H is to K. So that again, our 4 numbers, F, G, H, and K, they are in continued proportion, they all have the same ratio with one another as A has to B. And yeah, sorry, I was going to say a third thing about that, but that's actually just the next part of this proposition. So, now remember that A and B are the least numbers which have that ratio. We were given that, and so we can say by proposition 722 that they are, of course, prime to one another, which means by proposition 727 that their squares will be prime to each other and their cubes will be prime to one another. And remember, a squared makes c, b squared makes e, so a squared is prime to b squared. That means that c is prime to e. And for the same reason, a cubed makes f and b cubed makes k, so f and k are prime to one another. And you'll remember in the previous proposition that if any number of numbers be in continued proportion and the extremes of them, the numbers on the ends, are prime to one another, the continued proportion is least in that ratio. And so we can say because C is prime to E, the geometric sequence or the continued proportion of C, D, and E is the least with the same ratio as A and B. And for the same reason, because F and K are prime to one another, we can then say that, because F and K are prime to one another, we can say that the geometric sequence or the continued proportion of F, G, H, and K is also least, which have the same ratio as A and B. And these are the sequences, these are the continued proportions that we wanted to find. We wanted to find a 3-term continued proportion and a 4-term continued proportion, which has the same ratio as A to B and is the least with that ratio. And we've just found that in the 3 numbers C, D, and E and the 4 numbers F, G, H, and K. So we can say we are done with the proposition Q, E, F. There is a porism appended to this proposition. What it says is that if 3 numbers be in geometric proportion and are least, not geometric proportion, continued proportion. So if we have a 3-term continued proportion and it's the least with that same ratio, then the extremes are squares. And on the other hand, if it's a 4-term continued proportion, which is also least, the extremes will be cube numbers. That is what the porism says. And we see that because in the 3-term continued proportion, C, D, and E, which is the least with that ratio, C and E are both squares, C being A squared and E being B squared. And we see the exact same thing with F, G, H, and K. They are continued proportion. They are the least with that ratio. And we recognize that their extremes, F and K, are both cube numbers. F being A cubed and K being B cubed. Of course, it's always helpful to see particular examples of this proposition, so let's just go through one of them. Say we had a given ratio 2 to 3, and what we wanted to find was a 3-term geometric sequence or a 3-term continued proportion that has the ratio of 2 to 3. Well, how we would do that, we would start by taking 2 times 2, which is 4. Next, we would take 2 times 3, makes 6. And finally, we would take 3 times 3, or 3 squared, that would make 9. And this is a geometric sequence. It is a continued proportion, and that 4 is to 6, just as 6 is to 9. And we can say that it is the least which has the same ratio as 2 to 3. There's no smaller set of 3 numbers that you can put in a geometric sequence that is less than 4, 6, and 9. Now, if we wanted to find the 4-term continued proportion that is least with the same ratio as 2 and 3, what we would do, we would take 2 times 2 times 2, or 2 cubed. That would be 8. Next, we would take 2 times 2 times 3, so 2 squared times 3, that is 12. Next, we would take 2 times 3 times 3, that is 2 times 3 squared, that makes 18. And finally, we would just take the cube on 3, so 3 times 3 times 3, that makes 27. And what we can say because of this proposition, because of how we've made these geometric sequences, we know that 8, 12, 18, and 27 are the least numbers that have the same ratio as 2 to 3 in a continuous 4-term proportion. That is that 8 is to 12 just as 12 is to 18, just as 18 is to 27, and all of those, or each of them on their own, are to each other as 2 is to 3. Furthermore, we also see that the porism holds, in that because 4, 6, and 9 is a 3-term continuous proportion, the porism tells us that the extremes will be squares. So the extremes here would be 4 and 9. These are obviously square numbers. And the same thing follows for 8, 12, 18, and 27. We recognize that 8 and 27, they're both cubed numbers. 8 being 2 cubed and 27 being 3 cubed. So we not only see that the proposition holds and that this is a valid way of constructing such sequences and such continuous proportions, but we also see that the porism appended to it is also true. That, I don't know what else you would ask for from, from a video demonstrating this proposition. So I'll just end the video here and move on to proposition 8.3.